everyone, welcome to part 12 of my video series on statistical significance testing. So in this video, we are going to talk about Lilliefors testing or normality testing. Now, first of all, I want to make this very clear. If you want to get some output from this video, you must visit my previous video of this series, which is based on the KS test or Kolmogorov-Smirnov test. It's a very hard name, but anyway, the brief name is KS test basically. So you need to actually watch the KS test video first, because this test is a special case of the KS test. So I'm going to put the link of that video in the description of this video. Okay, so let's dive in. So first of all, we heard about the one sample KS test in the previous video. So in the previous video, we said that one sample KS test asks this question: does my data, the data set that I've collected, follow a known distribution? So that known distribution can be normal, Poisson, uniform, and many other things. Okay, so that is the thing. Now, the thing is, the normality test that we are going to describe today is specifically for normal distribution. Now, you may ask that already KS test is there, which actually works on all possible distributions. So why do we need a special test like normality test for normal distributions? So that is what I'm going to motivate you guys first. So there are two types of one sample KS test. So in number one, in one case, you can assume a fixed normal distribution. For example, you can say that, okay, suppose my normal distribution has a mean 0 and standard deviation of 1, and then you can compare your data set. You can compare your data, my data, this one, against that. This is number one. And case number two, you can derive mean and standard deviation from this data, from your data, and compare your data with that specific normal distribution. So these are the two ways you can actually do the KS test. Now, what is the issue with these two types of KS tests? So let's see that. So first of all, this is a fixed distribution. So you can see that when we assume a fixed normal distribution, this distribution is fixed, and this distribution can be very far even from many different normal distributions. So suppose there is a normal distribution with mean 5 and standard deviation of maybe 3. That will be very, very different from this mean 0 and STT equal to 1 distribution. So they are obviously going to be very far, and so your result is going to be statistically significant, and so you are going to say that these two distributions are actually different, when it is actually not, because both are normal distributions and they are not different. It's just that their parameters, mean and steady, mean and standard deviation, are actually different. So it does not tell us anything about normality. That is the first point. Now let's see case number two. What is the problem with this one? In case number two, the normal distribution parameters are actually inferred from the dataset itself. So we said that the mean and standard deviation are actually being obtained from the data. So they are obtained. So the normal distribution itself is being obtained from the data, and that is why the distance d that is going to be calculated, which is done in KS test, is going to be smaller than it actually is supposed to be, and it will give us an artificially lower p-value. But we don't want this, right? We don't want this overfitting kind of thing where we are actually making the normal distribution based on the data, and then we are artificially making the distance d smaller. Now, if you guys don't know what I'm talking about here, about distance d and all of these, then you must go back to the KS test in the previous video, which I left the link in the description as always. Okay, so the idea behind the normality test is this. First of all, it is a variant of case 2. It is a variant of case 2, so you definitely do this. But this artificially smaller d value is handled here. So how it is handled is like this. It simulates how likely it is to get distance bigger than or equal to d if we generate same size data sets from the normal distribution and calculate distances from these data sets. So what do I mean by that? It's a very big sentence. I will actually break this down gradually. But just to make things clear right here, what is happening here is basically you are doing this simulation, this case 2 simulation many times. You are doing this many times, and after doing this many times, what you are doing is you are calculating the simulated distances, and you are trying to see how likely are those simulated distances to be bigger than or equal to d, which is the actual distance, right? If it is actually highly probable, if it is very common for those distances to be this big, then it is not statistically significant. We cannot reject null hypothesis. That means the distributions are similar. But if you see that those simulated distances are actually much smaller, right? I mean, that means it is very uncommon to get this type of large distance in simulation. That means that this is statistically significant and we can reject null hypothesis. So let me actually take you through all the steps here. So first of all, this is our null hypothesis that my dataset follows normal distribution. And the alternate one is my dataset distribution is significantly different from the normal distribution. So these are the two hypotheses. Okay. Step number one is you feed the parameters on your real data. So you have your dataset, you have all the data points. So what you do is you compute the mean and standard deviation from those. And suppose your dataset size is 50. That means in your dataset you have 50 samples, right? That is why n equal to 50. Okay, that is very simple, nothing complicated. The next thing is you compute the observed D. So what you do is you calculate the ECDF, the empirical CDF from this data. You calculate CDF of the normal distribution, which has nu and sigma as parameter. You do those two things. And based on those two, you get the D, the distance D, right? So again, this we have talked about in detail in the previous video. Okay, now this is the new part. Now you have to run some simulations. Maybe you are running 10,000 simulations. Now, how does one simulation look like? So in one simulation, you randomly take 50 samples from a standard normal distribution. Now it doesn't have to be standard normal distribution. It can be any normal distribution, but normally people use the standard normal distribution for simplicity. So you randomly take 50 samples from standard normal distribution, right? Why 50? Because you have 50 samples in your data set. Then you estimate the mean and standard deviation from these sampled 50 samples that you actually randomly sampled. Now, ideally, this mean and standard deviation should be 0 and 1, but it will not be like that because you have only 50 samples. It will be a bit different. After doing that, you are going to calculate D, right? So how would you get the D simulation? By using the normal distribution of carrying this mean and standard deviation and using these 50 samples, just like point number one. Just like point number one, you are going to get that D, you are going to compute nu and sigma, and just like point number two, you are going to get the D, right? But only this time that 50 samples are not your data set, they are simulated, and the mean and standard deviation is also coming from the simulated, and the normal distribution CDF is calculated from this mean and standard deviation. So right now, if you do this exact same thing 10,000 times, you are going to have 10,000 DSIM values, right? What you have to do is you have to see how many of these DSIM values are actually greater than or equal to your D observed, right? So suppose only five of them are actually greater than or equal to D observed out of the total 10,000. That means p-value is going to be very, very small. That means you can reject your null hypothesis. That means your dataset distribution is actually significantly different from the normal distribution. So this is basically the normality test. If you like the video, feel free to subscribe and share, and you can donate to our channel if this channel helps you in any way. Thank you very much.